All right, in this video I'm going to be proving the change of variables formula, okay? The Jacobian change of variables, hopefully you watched the last video, and I said for a, given change of variables where we're going to take in u's and v's and get back x's and y's, okay? So this is where we're going to switch from x and y to u and v. If I have, this transform that is going to be C1, okay, so I don't necessarily need it to be a linear transform like we had in linear algebra. I just need it to have continuous first partial derivatives, where t takes u and v to, some g of u and v and h of u and v. And I need to point out that when I say g and h, what those are what we would consider x and y. Okay, so I'm just going to say that's x and that's y. Okay. What we do is we're just going to, kind of change variables. Change our region according to that change of variables, and then we're going to have to adjust dA by some sort of factor. Okay? And I'm going to prove this to you, but first I'm going to kind of go back to AP Calculus and remind you of something and kind of show you that what we're doing here is actually going to be the exact same as what we did all along. So what I want to talk about is a definite integral. I'm going to talk about, so I'll come back with the proof. Okay, the definite integral from 0 to pi of cosine of 2t dt. And I'm intentionally not using u because the way that we do it in the single variable class can maybe feel a little backwards from this. And then, just while I'm thinking about it, we're definitely going to want our transform to be, we want it to be invertible. We're going to want to be able to go forwards and backwards with this transform. But, for the most part, I wouldn't set you up in a situation where you needed to use a transform that was not invertible. So, anyway, I'm going to draw a picture of this integral, right? I can do that. Cosine of 2t, it's like cosine of t, except it traces out twice as fast, right? So, and so it's, this much area. Okay, and I'll also label this as pi. All right, well, if I wanted to change into x's, right, because, I don't know, maybe, at the beginning it was too much to just think of an antiderivative for that. If we wanted to change to x's, what you could say is, what if x was equal to 2t? Well, then we said that dx was 2 dt. And what was actually more useful to us was that dt was half of dx. And now I'll come back and, actually do that. But what I'm going to kind of go over here is say, if I change this into x's, okay, maybe that's pi, and that's 2 pi. This is a t world versus an x world. All right, really what I'm going to do is and if I was to take, just like basically one of these grid squares and compare it to one of those grid squares, really what I've done is I've done that. So, maybe I'll grab a different color real quick. So this small square, after the transform, is looking like that. And that may be a little exaggerated, right? But I'm, envisioning it's twice as big. So to account for that fact, if this is kind of the same image, more or less, one full period of cosine, I want to find the area underneath it. Well, I have to account for the fact that my area's got twice as big. And so what I do is that's where that half dx comes in. And so what I'm really doing is I'm saying that this is the same as the integral from 0 to 2 pi of cosine of regular x, but dt was half of dx, and that's where I'm going to scale that back down so I can make this the same area under the curve. So times 1/2 of dx, okay, because it's half the area. Okay, what I'm trying to show you is that this is the exact same thing, except where, I'm going to have some sort of like scaling factor on my area, and that's going to be the absolute value of j, where j is some determinant of partial derivatives. Okay, and I'll just kind of naturally come to that over the course of the proof, and I think you'll be able to understand where I'm doing here. All right, so I'm going to get rid of this, and I'm going to prove that. Now, before I prove this, I don't really know where I'm going to be putting this, but I do need to like kind of point out a fact to you from, I think I've actually mentioned this before in a different video in this course, kind of the same nature, but I'm going to need to use a fact about the definition of the derivative. Okay, remember that for small delta x, the partial derivative of f with respect to x is equal to, or at least approximately equal to, at the stage where I'm doing the approximations, f of x plus delta x and y minus f of x and y all divided by delta x. Which then means that if I just have an f of x plus delta x and y minus f of x and y, without this divided by delta x, I can say that's like fx times delta x. And that's going to be big for us today. So what I'm going to do is I'm going to start off by looking at t. I'm going to start in UV world. I'm going to map into XY world and kind of track the difference in a small piece of area. Okay. So oh, right. Hold on, what was I thinking? Oh yeah, UV world. Okay, so U and V. Okay, so I've got this point A, and I'm going to be writing down a bunch of points and then kind of like listing down below facts about them. And so point A, I'm going to call that U and V. Okay, and then I'm going to go over here into X and Y world. Okay, and so this is what happens after I apply T, right? That's what T does, is it takes U's and V's and it gives you back X's and Y's. Okay, so after T, I've got, I don't know, some point P. So I'm going to say that P, that's not F, it's T of A, which is going to be, all right, what happens to U and V after I run it through T? T does G to the U coordinate and H to the V coordinate, right? Well, all right, so that's G of U and V and H of U and V. Okay, and then what I'm going to do is I'm going to add in points B and C to kind of fill out a, my little differential piece of area, right? Because this is going to be delta U, that's going to be delta V, and this is going to be delta area. Okay, and all right, hold on, just got lost myself. Oh yeah, this is delta V. So B is the point where I've done U plus delta U but left V the same, and C is where I've left U the same but done V and added a little bit of more. All right, and so what I'm going to be interested in is the image of B and C under T. What's going to happen to those? Because I'm going to have basically these two vectors. I'm mainly interested in the image of the vector AB and the vector AC. What's that going to look like? And then I can use those vectors to find an area of the parallelogram that's kind of spanned by them. And so what I'm going to say is, maybe I've got that, and I call that Q. I call this R. Okay, where Q is T of B. And R is T of C. All right, now this is going to be a lot of U's and V's and H's and G's here, but it's going to clean up pretty nicely. So when I take B, I just need to do, okay, so it's g of u and v plus delta v. Okay, hold on. And h of u and v plus delta v. All right, that's a lot, but what I really am interested in is the vector pq and pr. Because if I can, let's see if, that's not very good. No, something like that. If that's the parallelogram spanned by these two vectors, this would be like the effective delta area. Right? All right, so now what I'm going to do is I'm going to write down a formula for vector pq and a formula for vector pr. Okay, PQ is just really Q minus P. So if I take, and I'm going to write this one vertically. So in the x coordinate of Q minus P, I'm going to have G of U plus delta U and V minus G of U and V. Well, what that is that's the partial derivative of G with respect to U times delta U. Okay, and maybe I'll do this one the once. Okay, so it's PQ is Q minus P, at least in the x direction. So G of U plus delta U and V minus G of U and V. I'll let you look at that for a second and kind of reconcile this with that. Okay, so basically I have GU is equal to G of U plus delta U and V minus G of U and V divided by delta U. Except I don't have this delta U in a denominator, so I multiply it over and I have GU delta U. Okay, I'm going to do that and I'm going to kind of leave the rest of them, treat those as self-evident. Okay, so I've got GU delta U. Over here I'll have HU delta U. And I'm just going to point out that because I'm going to eventually want the area of this parallelogram, which I feel like you really can't see very well on the screen, but since I'm going to want it, I'm going to need to take the cross product of two vectors, which means that I will just turn it into a three-dimensional vector. So I'll just assume that we're sitting in the xy plane. And then PR is going to be, it's going to be the same with the delta v's, if you look at it, right? Because R is where I've got inducing these delta v's, and so the exact same thing is going to happen. I'm just going to have GV delta V, HV delta V, and 0, right? So the area of this parallelogram, so delta A prime is equal to the length of PQ crossed with PR. Now, this will actually be easier than you think to compute this cross product. I'm going to set up for it right here. But the fact that both z terms of these are 0 is going to make this really, really nice. IJK, okay, GU delta U, HU delta U. And GV delta V and HV delta V. Okay. And so really what's going to happen, I've written this really small because I think that, you know, if you're just following along, think about, you cover up I, I'm going to have 0 minus 0, J, 0 minus 0, K. So this is equal to the length of the vector that has the first two components are 0, but then the third component is going to be the determinant of, you know, this little submatrix. Which is, you know, really what I'm calling J. I'm going to point that out. That's the first time we're going to see it. Right, this is, you know, if you think of G equals X and H equals Y, maybe I'll actually go in and do that. Yeah, I think that would actually be smart. So I've got I, J, and K. These are both zeros. And, you know, I don't even know if you can read this on screen. G is X, so it's XU delta U, YU delta U, And then xv delta v and yv delta v. And then when I go and I do this, I'm going to have delta u delta v, just trying to squeeze too much in, too small of an area, and then this is j, as I've written it up there. I'm not going to be able to fit it, but I think that that's a sufficient justification. dxu, xu. And so, the length of this vector here, I'm going to clear out the stuff I don't need so much anymore. And this length is just going to be, well, if I have, a vector that's 0, 0, 10, that has length 10. Okay, so this is going to just be j delta u delta v. And since we're talking about the length of a vector, that needs to be positive. Okay, so we really, since this determinant can be negative, right, I'm going to say it's the absolute value of j, delta u delta v. Which is equal to, if you think about over here, delta u delta v, that's delta area. Okay, so I'm going to say that this is equal to absolute value of j, delta area. And then, of course, as delta u and delta v go towards 0, the approximation improves. Delta a goes towards dA, and we have the absolute value of j dA, which is what I'd set out to show in the first place. Okay, I think that that is a very detailed explanation of where we're getting this Jacobian determinant from, but it's actually not, I don't think it's that hard to draw pictures of, at least in the z equals f of x and y case. Okay, I can definitely say this for higher dimensions, right? I could get something like this for triple integrals. And in fact, I think in the previous video, I verified the dv for spherical coordinates because I wasn't really able to draw you the picture of it, so I just computed it using the Jacobian. So we can do this on triple integrals, but the proof is going to be, it's going to be a level higher. It's going to be an analysis level proof. I'm going to have to invoke, I forget, like, some kind of theorem we don't have yet. An analysis level theorem. But this, for double integrals, I feel like is right at Chell's level. So I figured I'd explain to you where are we getting this Jacobian determinant from. And it's really from, the way the partials are interacting with the partials of the transform are interacting on delta area. Okay, that's it.